Did they come to a specific door? I forgot to ask Lisa this.
Sorry?
The people who don't have an ID card, do they know to come to this door?
I don't know at all.
Okay.
I don't know if there's any.
They come from this door.
I think they do. I just didn't want to make sure I don't have people waiting at the many other doors to this building. Okay. So, thank you.
What is the heavy exotic?
This is a pheno thing.
Huh?
I think it's a pheno thing.
Oh, okay. But it's
Like,
4 quark states or something like that.
I suspect so.
Yeah, so-
What exotic configuration of quarks.
Give me one more. Oh, I can't downstairs. So
No?
How are you doing?
Hey, how are you?
I don't want to see you in person.
I know. Well, good to see you in person, yeah. We'll be at Rutgers next week, I think, Thursday.
Oh, is that right?
Yeah, it was the condensed matter, Pierce Coleman's.
What time?
Well, I'm there all day, but the seminar's in the afternoon, I think.
Yeah, because I have to leave in not too
Or is it
late afternoon.
Tuesday or something? Actually, I don't know this conversation being broadcast. Mario, can you put the screen on the broadcast?
What's that?
The blackboard.
You want the blackboard up there?
No, but that's being sent out.
Yes.
Oh, okay. Thank you.
Yeah, this TV is only what you're seeing.
Yeah, okay. I don't see it on my computer.
Are you connected to the call?
Yeah, There's an IAS person, but it's just blank.
It's blank.
Yeah.
Yeah.
Oh, now it's okay.
Good.
Now it's good. Yeah.
Sabir, do you have, so the recordings, are they being edited before they're posted? Or
No.
they just go up in there?
I just do that myself. I just
Oh,
on
okay.
YouTube.
Do you want us to do that for you?
Sure. It's my. I mean, I have to give you access to my YouTube channel.
We have, I mean, if you're free to do it on your YouTube account as well, but we record quite a bit on campus and we post everything to the Institute YouTube channel.
Sure, absolutely. Then I can just link it from my channel.
Yeah,
Oh, of course.
I'll send you some examples of what we've done, and if you want to do it that way.
I'm sure it's great. Go ahead.
Okay.
Yeah.
All right.
You put like a way in the beginning, a promo or something.
We have a slide that shows the Institute seal, and then it transitions into some title screens and then into the video.
Oh, cool. Okay.
And then we also chop off like the front and the end and like clean it up a little bit.
Right.
Okay, I'll make myself a note and we'll do the ones we've done so far plus this one. And then
All right, great.
the rest going forward.
Okay, good morning. I hope you can hear me in Hyderabad and Mumbai and Bangalore. Screen. Hi. Okay, great. So let me just recap where we were last time. We were talking about the Bose-Hubbard model, just defined by these equations: bosons hopping on some lattice with on-site repulsion U, helping matrix element W, and a chemical potential mu. And we sketched the space diagram that we drew out of, made out of some perturbation theory, some mean field theory, and then we also talked quite a bit last time about the nature of the phase transitions. That may be a bit technical, especially for the beginning students. So don't worry about that part because we're not going to say much about phase transitions in this course. But anyway, to recap the phases themselves, there were two basic phases. There's a superfluid phase where there's a global U1 symmetry in this Hamiltonian of Bi goes to Bi times e to the I5. And the ground state locally picks a definite phase, and that phase characterizes the superfluid order. There are gapless excitations, meaning that there are density fluctuations, whose energy vanishes as the momentum goes to zero. It's compressible, meaning that if you change the chemical potential, the density can change. Okay. Something being compressible is, a very special thing at zero temperature. At finite temperature, everything is compressible. There's always some change, thermal excitations that come in when you change any parameter. But at zero temperature, compressible phases, strangely enough, are kind of hard to find, and this is one of them. And then I already mentioned the broken human symmetry. Then we also had at strong interactions, these insulators. Usually they're called mod insulators. If your definition of a mod insulator is an insulator that requires interactions to exist. If that's your definition of a mod insulator, then this is a mod insulator. For bosons, in fact, Every insulator is a Mott insulator because bosons, you cannot get an insulator without interactions. For fermions, as we'll see very shortly, you have the concept of a band insulator, which exists even for free fermions. So then what you call a Mott insulator becomes a little more meaningful. Anyway, so let's just call it a trivial insulator, but I say Mott because many, if you read many papers, they'll call this a Mott insulator. Anyway, so in the Mott insulator, you have the particles localized, exactly one particle per site on the average. Because this is not the exact wave function. The wave function will have some fluctuations where this particle hops there and then hops back. That's part of the ground state, and those become more and more important as you increase the value of W. Ultimately, there's a phase transition, which we said more about yesterday on Monday. And then you can get Mott insulators of 2 particles per site, 3 particles per site, and so on. All right, any questions from on that quick summary? Yes.
You actually had 2 versions of the superconductor fluid with a positive or negative coefficient for one term and the one effective interaction.
Yes.
And I was wondering if both of them have experimental realizations.
Yeah, sure. I mean, you can, so in cold atom systems, you can, in fact, people see this Mott insulator. And if you increase the density, if you add a few particles, then you'll have the superfluid here, which will be the superfluid of these moving particles. So in some sense, the superfluid stiffness here and the dense, the superfluid density, really speaking, but more precisely, the superfluid stiffness here will be due to particles, and it will be quite small. It won't measure the full density. Unlike in the continuum, as I mentioned in the very first lecture, the superfluid stiffness is related to the full density of helium atoms, for example. Helium atoms interact very strongly in the continuum, but that doesn't deplete their superfluid density or stiffness. Here, because you're on a lattice, there is a depletion. The superfluid stiffness is very small, and it's due to these extra particles moving. But you could also be, I'm sorry, I had the wrong way around. This is where the density is a little bit bigger than 1. So that's what this corresponds to. But you could also be here, where you remove a few particles. And then that's a superfluid of holes, of these holes moving around. And yes, absolutely, I think those things are seen in cold atom experiments. If they're smoothly connected, there is no fundamental difference. It's just a question of what is the, what are the low energy degrees of freedom on a microscopic scale? Are there holes or particles? But the symmetry that you're breaking is exactly still the same symmetry. Okay, great. Any other questions? Especially on the students in India. Okay, so before leaving the Bose-Hubbard model and going on to the electron-Hubbard model, I want to say a few more things, and especially want to focus on this case here, where the density is 1/2. So suppose we're looking at the system where the density is 1/2. Somehow you arrange things that exactly half the sites are occupied. So what happens there for this Hamiltonian? Let's just put W equal to 0. So then all you have to do is just look for minima of this interaction. You fix the total density, so even this term doesn't make any difference. So you simply have to make sure to minimize the energy that there's never more than 1 particle on each site. And then this will give you 0. So how do you do that? So let's just take the case of a square lattice. So there's many ways of doing it. You just fill half the sites. So you fill them in any way you want, exactly half of them. And the number of ways you can do this is, of course, n factorial over n over 2 factorial squared. That's exponentially large in n. And so for this Hamiltonian at density 1/2, which is, will be somewhere here, well, we don't have density, this is chemical potential, but this is where such a state may exist. There's a huge exponentially large degeneracy. And so obviously that's very, very different from these trivial insulators, but there was no degeneracy. There were unique states. Here we have a huge degeneracy, and a big part of the course really is understanding how the degeneracy is lifted. And the many different ways you can lift it. Now, one way to lift it is we just put in some repulsive interaction. So suppose I put in some interactions, not even nearest neighbor, they could be longer range, Bij and INJ. They could be repulsive or attractive, but you add a few more terms like that. So then, and you agree that the density is 1.5. And let's just stick to W approximately 0. Then how do you find the ground state? Well, the ground state then becomes a classical problem. You take this energy here, and you minimize this energy. We call this the classical energy. And you minimize it over all possible integers and I, subject to the constraint that someone and I is n over 2. So you define, well, sorry, is ni equals 0 or 1. No, you could also, in principle, if v is much bigger than you may even want to put more than one particle per site. So this becomes a classical problem of minimizing some complicated function over integers. So that might seem, like a much simpler problem, but it is not. That's in fact an example of a very difficult problem in computer science. It's probably, I think, it is NP hard to find the global minimum of some function like this over the set of integers. Traveling salesman problems and various other optimization problems can be restated in that manner. So even finding the classical ground state is a very difficult task. But let's just look at a very simple case where Vij is nearest neighbor. So it's equal to V for Ij nearest neighbors. And greater than 0. Well, in this case, it's clear what the global minimum should be, at least on the square lattice. And that's very easy. You just have to avoid the particle. You want to minimize this. Therefore, you don't want two particles on the same site. And if you want to minimize this, you don't want particles on nearest neighbor sites. And now, instead of having this huge degeneracy, the total number of states is not that large. It's just 2. There's only 2 possibilities globally. It's basically the chessboard configuration. So this configuration now, on the checkerboard of the chessboard, is a global minimum. It has essentially 0 energy because this term is 0, and so is this 0. Right? These are all positive numbers, so it can't go below 0. So that's the minimum, but there's 2 of them. So now it's not this degeneracy, but 2-fold degeneracy. Okay, so now you can start with this state. So you pick one of them, and then you do perturbations in W. And you'll find it's all well defined. You can look at, there's a gap, and to both particle and hole-like excitations. And this is a perfectly stable ground state. And it's also an insulator. For small W, W much smaller than both U and V. And so you've got another insulator here, which is stable once you put in the V. And so maybe I can just stick it in here. Once you have a non-zero V, then there's another insulator here, which is, say, the checkerboard. I don't know exactly what phase diagram will look like, but there's a checkerboard. Let me just draw a checkerboard. There. Okay. All right, so we found an insulator at another density. So that seems like a step forward, something different. But in some sense, this is not really fundamentally different because in this state, you've broken a symmetry. You've broken the symmetry of translations where this site is not equivalent to this site. And there's another state where the densities are reversed. So there's a twofold degeneracy. And there's an autoparameter. In this case, it would be just an Ising autoparameter. So it's very similar to a ferromagnet, which in point all spins up or spin down. Here, there's two possibilities for the checkerboard pattern. Also, very interestingly, you can now ask, what is the unit cell? So this is some periodic arrangement, but because of broken symmetry, there's a unit cell now, which describes the structure and all of its properties. Well, there's many different choices for the unit cell, but one choice would be this unit cell right there. And when you repeat this, when you translate it along the diagonals, you can reconstruct the whole structure. So there's a perfect periodicity. This pink diamond looks exactly like this one, and so on. So that's the basic unit cell. And the area of this unit cell is twice the area of the original unit cell. So the unit cell has doubled in area. And what's the number of particles per unit cell? And the density per unit cell is still 1. It's not 1/2. So you've broken the translational symmetry, you've made the system have a bigger period, and you got something at density 1/2, but it's only density 1/2 with respect to the Hamiltonian. It's not density 1/2 with respect to the actual state you obtain in the lab. It's still 1 per unit cell. Yes.
So you remember the Z2, and you said it's a little bit like Ising, but
Yeah.
there's an important difference that this Z2 is translation. In the case of Ising, it's an internal symmetry.
Sure.
Is this important for any? Is this distinction important for anything?
It can become important in a few subtle cases, I imagine. But when you look at the leading order field theory terms, it's not important. It behaves just like an internal symmetry. But there could be, subtle anomalies that you may have to worry about in some cases. Yeah. Okay, so the point I was making was this is really, in the end, not really a fundamentally new type of state. It's still a state with an integer number of particles per unit cell. You have to break a symmetry to form that state, but okay, but it's very, and many of its properties, unless are basically connected to that of the trivial insulator. There'll be some difference in the nature of the phase transition, but we won't get into that now. But as a state, as a phase of matter, it's not generally just different from the integer states. Okay. What else was I going to say here? Right. So that still leaves open the question: can you get an insulator at n equals 1/2 without doubling the unit cell? Okay, is such a thing possible? And the answer to that, as I've mentioned earlier, is yes, but only in 2 dimensions and higher, not in 1 dimension. And of course, we're going to spend a lot of time discussing that possibility. But it's good to be aware of this possibility. Also, you can think of this, this particular state is somewhat similar to solid helium-4. Now, ordinary helium in the continuum has a continuous translational symmetry, unlike this Hamiltonian, which has only a discrete translational symmetry. So helium-4 can form a superfluid, as can these bosons. However, these bosons can also break the translational symmetry, like in this state. They broke a discrete symmetry to a slightly different discrete symmetry. And then you got an insulator with an even number of, with an integer number of particles per unit cell. The helium-4 does the same thing. It breaks a continuous translational symmetry to a discrete symmetry. And the number of helium, and so it can have a unit cell of any size it wants. But the number of helium atoms per unit cell in solid helium-4 is an integer. So that's the fundamental characteristic of the solid, is that there's an integer number of bosons per unit cell. And that's also this true here. So this is like a discrete version of a solid. But in this case, you're breaking a discrete symmetry to another discrete translation to another discrete translational symmetry, whereas in solid helium-4, you're breaking continuous translational symmetry to a discrete translational symmetry. Okay. And the transition from solid helium-4 to the superfluid is first order, and that could well be the case here too. You could get an intermediate state, which is rather difficult to observe, and there are some instances that maybe it's been observed, called a supersolid, where you do both. You break a discrete translational symmetry, and also you break the U1 symmetry. You could break a discrete or continuous translational symmetry. It's pretty clear helium-4 doesn't do that, although there's still some lingering claims it might, but I don't think they're very convincing at this point. Okay. All right, so I think that is pretty much what I wanted to say about the Hubbard model for now. As I said, we're going to return to this and look at this n equals 1/2 case in much more detail, where we'll find a new type of state where you don't have an integer number of particles per unit cell, but you still have a gap. Yes.
Presumably on triangular lattices and so on, there are issues with frustration in these models.
Yeah, so right. So for example, if I took this model in the triangular lattice, you would still have an exponentially large degeneracy. Then you have to put further interactions to reduce it. Right, and then then the question, an important question is, how, suppose I did have an exponentially large degeneracy, how is the degeneracy lifted? So you can lift it by entropy effects by just raising the temperature, and that's sometimes called order by disorder, where there's an entropic selection of various states. Or you can have interesting quantum effects, which is what this course is about, really. How you lift these degeneracies, at least the first part of the course. Yeah. All right, so let's go from here then to the, so for the Bose-Hubbard model, there's still, as you can see, many open questions down here, especially when you add further interactions. But out here, I think things are extremely well understood. But for the Fermi-Hubbard model, or the electron-Hubbard model, even the most basic things are still not understood. So it's conventional to call it T rather than W. I sigma, C sigma, that's summation conjugate. And then there's plus someone I minus mu. Okay. The way people normally write it, Ni up, Ni down, plus U, Ni up, Ni down. Okay, so this is the basic Hamiltonian we're going to be looking at for quite a while. It's an excellent starting point for describing many materials, including the cuprate superconductors. Yeah, it probably contains much of the answer to many of the mysteries of the cuprates. Maybe not all, maybe you need to add a few other terms and to get complete agreement with experiments. But many of those, theoretically, there are many theoretically open questions for this model. So let me first define everything here. So sigma is a spin, it can be either up or down. It's just some flavor label. It has nothing to do with rotations in space, at least at this level. You have to put in spin-orbit coupling to connect rotations in this spin space to a physical space. So let's see, and then these are Fermi operators, so they're anti-commute. Ci sigma, J sigma prime. Commutator is delta ij, delta sigma prime. And similarly for the other operators, which I presume you know. And of course, Ni sigma is the number of particles with spin up or spin down. There's no sum over sigma on the right-hand side. Okay. The first thing that might confuse you is that this Hubbard interaction term doesn't look spin rotation invariant. But it is, so this is the way you write it. And it is spin rotation invariant. And the reason it is, well, there's many ways to see it. But one thing you might notice is that, how about if I wrote it this way? U times Ni up plus Ni down. Right. So that looks with spin rotation invariant because this is the same as C dagger I sigma, Ci sigma, sum on sigma, whole squared, and then a sum on I. So because of the sum on sigma, this is clearly invariant under SU2 rotations in sigma space. Okay, so but what is this thing? Well, if you just expand this out, it's U times Ni up squared plus Ni down squared plus the term we keep, let me call it U bar times 2 Ni up, Ni down. Okay, so this is spin rotation invariant, as is this expression here. But now Ni up or Ni down has only two possible values. It's either 0 or 1. The Pauli exclusion principle. And when for those two possible values, Ni up squared, so that implies that Ni up squared, Ni sigma squared is just Ni sigma. Because there's only two numbers for which that's true. And so this thing is just gets absorbed into the chemical potential. Okay, so this doesn't break any spin rotation symmetries. There are other ways of seeing it, but that's one way to see it. Okay, so this is one of the things that I think condensed matter physicists do to confuse the particle physicists, writing in this horrible way that hides the symmetry. But anyway. Okay, so we want to draw a phase diagram much like this for this Fermi-Hubbard model. Any questions on what the model we're studying? Okay.
To erase one of the U's.
Oh, thank you. Yes. Okay. All right, so we want to draw a phase diagram like this, but we have much space here. So mu over u versus p over u, let's say. So just like the Bose-Hubbard model, let's just look at two different limits. Let's look at the limit of very large u, where t is 0. So then it again becomes a problem of just minimizing this function over integers. I have two integers on every side, Ni up and Ni down. And in fact, it's only two possible values, 0 or 1. So, so the answer is really very simple. I don't have the numbers on top of my head, but there's only three possible states over here. There's a state where everything is empty. So here, Ni up is equal to 0 is equal to Ni down. That's the vacuum state. And there's a state up here where it is Ni up equals to Ni down equals to 1. And nothing else. There's nothing above that. Unlike the boson that can go forever, here you can't put more than 2 particles per site. Okay, and so this is clearly a gap state. This is a trivial vacuum state. There's no phase boundary like this, presumably. And this is, as you turn on the hopping, it's pretty clear what this is. This is smoothly connected to the band insulator. So let me make it a bit more. Here, so there's two views then of this insulator. There's a state here where in real space, say the square lattice, you put spin up and spin down on every side. That's your ground state as u goes to infinity. How about here at very small u? How do you think of that? Well, now you have to think in momentum space. So in momentum space, there's a band of some type. It's only 2 dimensions, but anyway, I want to draw. There's only one band in this model. And this band is fully filled. So it's spin up and spin down, and all states are filled. So in this way of seeing, this is a band insulator. And this way of seeing it's a wave function that's totally local. And in fact, these are, because there's only one state, these have to be the same state. It's just different ways of writing down the same state. So this is really as trivial as the vacuum. This is the exact wave function, which is exactly equal to this, and there's nothing else. And that's this state here is simpler than that state. This state has quantum fluctuations when you turn on W. This one doesn't. There's only one state, and you can think of it either as in the local basis or in the band basis. So it's really the particle hole conjugate of an empty state, is this state up here. Okay, so that's the easy stuff. You have a band insulator, or you have the empty state. What happens in between? So here, where the density is 1, you don't want, what does the interaction say? That you don't want both spin up and spin down particles on the same site. But as long as you arrange that, then you're okay. So, but no, there's many ways of doing that, obviously. You can put a spin up any way you want. And let's say we agree that we want to have total spin 0 states, because we're not really interested in ferromagnets, although there's no problem with including that. So let's say we also say that sum on I up minus Ni down equals 0. So no ferromagnetism. Okay, so these are our states, and therefore if this is 0, the total number of spin up particles is 1/2, the total number of spin down particles is 1/2. And what's the total number of states? Well, it's exactly that. So the degeneracy of this state at integer filling of fermions is 9 n factorial over n over 2 factorial squared. In fact, it's easy to see there's a one-to-one mapping between this Hilbert space of defined here at integer filling, at filling 1, odd integer filling, that's the only odd integer around, is the same as this, because you could just say every time there's a spin up, there's a boson, every time there's a spin down, there's an empty site. So there's a one-to-one mapping between the Hilbert space. Of course, these are fermions, and the fermionic statistics will become important when you try to do perturbation theory in T over U. You can get very complicated terms that act on this Hilbert space. And those, will have the same form as things you could do a similar thing here, but they may have different, values. There may be certain ring exchange term have a certain sign for fermions, a different sign for bosons because of the Fermi minus sign, and so on. But there is a very close connection, which we're going to exploit between this problem and that problem. That really was one of the reasons I mentioned it. This insulating problem at integer filling, at unit filling, half filling, is very similar to the bosons at density 1/2, where the density of electrons is 1. Spin up and spin down, the density is 1/2. Okay. If you had ferromagnetic states, that will start corresponding to other fillings of the bosons, if you do the same mapping. Okay, so that's what you got here, 0, 1, and 2, which is not so different than from 0, 1/2, and 1 over here. They're very similar in the limit of infinite U. So how about at small u? What happens? Well, that's still an open question in some ways. It's probably the case that there is, in fact, a superconductivity at very low temperatures. But let's just put U equals 0 to begin with and talk about that case. I think I'm going to erase the bosons now. So small u and ignoring certain exponentially weak corrections related to superconductivity, but we will talk about in the next few weeks. So it's small u, you just free fermions, and really the only interesting thing is densities between the total density is between 0 and 2. And in fact, the cuprates correspond, the insulating cuprates correspond to density 1, and the greatest interest is what happens around 1. But so let's assume we're somewhere there. Then at small u, you just have free fermions. And so here I want to take the band picture. You have some band, and you're going to occupy states below some Fermi energy. So these states will be occupied. This is the Fermi energy. And you can draw a Fermi surface. This is a momentum space now. Right, so all the axes. And this is called the Fermi surface. And these states are filled. So these field states are the same as these ones here. This is a one-dimensional section along some axis like this. This is, sorry, I should draw and label the coordinates. This is K, and this is epsilon K, the energy of fermion hopping on that lattice with hopping T. So EK here, more precisely, let me write it on the square lattice. It's minus 2 T cosine KX plus cosine KY. Okay. So the Fermi surface is not exactly a circle, it's some complicated shape. We will say more about that, of course, again later. So that's the free electron state. And let's think about that a bit more. What are the characteristics of the states? And that's really the subject of the remaining part of today's lecture, which is the topic of Fermi liquid theory. But let me make some general remarks that you can just see by looking at it. So let's assume that this free electron state is somehow stable for small interactions. And in fact, it is modulo the BCS instability. What are some of the properties of the free electron state? Well, now I'm regretting I arranged the boson diagram. So there are some features here which it shares with the superfluid state. First of all, it's gapless. I can add particles or remove particles, excitations with essentially zero energy. I should put a mu over here. Yeah, okay. So in the grand canonical ensemble, let me make that point clear. So the Hamiltonian, I'm going to write as sum on K, epsilon K, C dagger K sigma, C K sigma. So I'm going to think in this language and put a minus mu inside here. So that U has gone to infinity, but mu is still there. Okay. And that's how I'm going to define EK. So I'm taking the grand canonical ensemble, and I just want to, at a given chemical potential, find the Hamiltonian, which has the lowest possible energy. So basically, you want to occupy states where epsilon K is negative and not occupy states where epsilon K is positive. So in this definition, the Fermi energy will be zero. It's good to think. So this is the locus of the curve, epsilon K equals 0. Okay, so mu has to be some positive number well, has to be in a certain range so that this crosses the band. Okay. So what are the excitations of this Hamiltonian with no interactions at all? Well, I can remove a particle somewhere close to the Fermi surface and create a hole. And in this grand canonical picture, that's going to cost me very little energy. It's going to cost me energy modulus of EK, and that goes to 0 at this on this surface. Or I can add a particle outside somewhere. That's going to cost me energy EK, which also goes to 0 as K goes to 0. So this is very similar to superfluid, where over the superfluid as the momentum went to 0, the energy for density fluctuation vanished. Similar in a Fermi liquid, as the momentum approaches the Fermi surface, it doesn't have to go to 0. So you have Gapless excitations, as K approaches the Fermi surface. So it's not a point, it's a whole surface. And that's really the fundamental distinction between a superfluid and a Fermi liquid. As K goes to 0, epsilon K goes to 0, and therefore I have gapless excitations. Now, if you insist on conserving number of particles, you could create a particle hole pair. You take a particle from here and put it there, and you can see that cause 0 energy. And the chemical potential cancels out of that. But it's kind of tedious to keep track of how many particles there are and making sure that the number of particles is always equal to the number of holes, because that's like a global constraint. So we don't worry about that, and just imagine we're in the grand canonical picture where we can independently remove and add particles at different momentum. Okay, so it's gapless. It's also compressible for the same reason. If I change the chemical potential, the Fermi surface will grow a little bit and the density will change. So here's another compressible state. dn d mu is not equal to 0. What are the characteristics the superfluid had? I forgot. It was gapless, compressible, broke no symmetry. No translational symmetry is not broken. There's no symmetry that's broken here. However, the superfluid did break a global U1 symmetry. This one doesn't. So that's the main difference between a Fermi liquid and a superfluid. The global U1 symmetry is preserved. Sorry, my board has become really messy here. Global U1 associated with particle number, which is Ci sigma goes to e to the I5, Ci sigma is preserved. So it's not a superfluid. It's sometimes called perfect metal, which is different from a superfluid because the symmetry is not broken. Okay. All right. So again, thinking about the weak U limit, we have now met two examples of states where we have of compressible gapless states. One is the superfluid with the broken U1 symmetry, and the other is this Fermi gas or Fermi liquid that we're going to discuss a bit more detail in a minute, which is also compressible, which has a Fermi surface. And near the Fermi surface, there are these particle and hole-like excitations, which, as we're going to discuss now, are well defined, at least asymptotically close to the Fermi surface. So just like for the bulk, we had this question in the large U limit, are there any other gap states, we asked? You can ask a similar question here. Are there any other compressible states of matter other than these two? Is there anything other than which don't break translational symmetry? I mean, a solid breaks translational symmetry. It's also compressible in the continuum. But you have a Fermi liquid here or a superfluid. Are there any other gapless states of matter which are not described, do not connect smoothly to these limits? Okay, so that's another topic of this course. In fact, the answer is yes. And of course, my favorite example is the SYK model, and we're going to come to that towards the latter part of the course. So that's really the topic of the course in some sense, to ask, are there gap states of matter other than those at integer filling? And are there compressible states of matter other than the superfluid and the Fermi liquid? And the answers to both questions are quite subtle and take us some time to develop, and really were not understood until relatively recently, what the different ways these things you can get other examples that violates the basic paradigms of the weak and strong conflict limits of the Hubbard model. Okay. All right, so with that introduction, let's just now dive into studying the weak U limit a bit more. Any questions in India? So, yeah, so let's just, I'm going to give you a gentle introduction to Fermi liquid theory. Call it Landau's Fermi liquid theory. Let me do that. Which would describe certainly the Hubbard model at VQ, except at very low temperatures, where there may be additional instability. I mean, Fermi liquid theory was developed by Landau, around the same time as the BCS theory, and he famously missed the fact that his theory was unstable to pairing. It's hard to, from looking back, it's hard to understand why, but these things always look much more obvious in retrospect. Okay, so our Hamiltonian will be some, the Hamiltonian just wrote down over here, E dagger K sigma. And the whole framework is very general, so we just say there's some interactions. And we're going to assume you're not in one space dimensions in any higher dimension. We're going to add some weak interactions to the free Fermi gas. And we're going to assume, like I drew over there, that in momentum space in 2 or higher dimensions, there's a surface at which epsilon k is equal to 0. Okay. So the ground state then obviously is all negative energy states occupied, epsilon k less than 0. And here epsilon k is greater than 0. So if I annihilate a particle in the ground state, this is going to give me the ground state, at least for 3 electrons, for k less than kf. This is just notation for being inside the Fermi surface, and is equal to 0 or k greater than kf. And if you want an explicit version, wave function for the ground state is probably on k less than kf, c dagger k up, c dagger k down on the empty state. Actually, in my initial discussion of Fermi liquid theory in the notes, I just dropped the spin. So I think I might do that. No, I didn't. It's there. Okay, maybe it isn't. At least when I teach it, I do often drop it to make my life a little simpler. In fact, I do later in the notes, so the notes are not consistent. Okay, so that's the free Fermi gas. Let's also make a plot of the excitation spectrum as a function of k. This is the, I should call it not EK. Oh, no, sorry, this is momentum. Yeah. K. This is excitation energy. So as a function, and you go through kf. And what happens? Well, if your k is greater than kf, you can add a particle, and that costs you energy ek, and that vanishes at kf linearly in some way. So this is ek, and this excitation is a particle-like excitation. And if k is smaller than kf, then you can remove a particle, and that's also going to cost you energy, but that energy will be modulus of ek. So this is a whole. Excitation energy have to be positive, otherwise you don't have the right ground state. And of course, this is ek over here, which becomes negative. But to get the actual excitation energy, you have to take the modulus of ek. So you have a very fundamental difference here, something very fundamental happening as I cross the Fermi surface. My elementary excitations will change their charge. They're, if these were charged particles, there are holes inside the Fermi surface and particles outside the Fermi surface. So the charge of these excitations, the quantum number they carry, the electron number, is discontinuous. It's -1 here and +1 there. So the essence of Fermi liquid theory in some sense is the claim that this distinction, where your elementary excitations change from being negatively charged to positively charged, is preserved even in the interacting system. There is a surface, and on that surface, inside the surface, your elementary excitation is negatively charged. Outside the surface, your elementary excitation is positively charged. And so that's the definition, colloquially speaking, of what is the Fermi surface in an interacting system. Because obviously these statements are no longer true. That's not the exact ground state once you put in interactions. And yeah, even this is not true in interactions. But the more precise statement is that the charge of the excitation changes on some surface. Yeah.
That's a zero temperature definition.
Absolutely. Fermi liquid has no, it's at finite temperature, the Fermi liquid is not a distinct phase of matter. It's smoothly connected to the classical gas, of Maxwell and Boltzmann. It's just totally smooth connection. It's only at zero temperature that there's a very sharp distinction. Yeah.
First line, did you mean C dagger C is on G is equal to G?
What did I do?
C on G equals G. Maybe I missed something.
Yeah, sorry. Yeah, you're right. It's not, well, anyway.
I think in the expression of the ground state below.
Yeah, no, that was wrong, of course. Thank you. Let me just call it G minus 1 with some state with one particle removed. Sorry, thank you. This is the correct statement. That's what I should have said. Yeah, I think that maybe let me say it better. Let me make a more precise statement. So this was correct. CK acting on G is 0, and here C dagger K acting on G is also 0 for, yeah. Okay, that's the better statement. Thank you. All right, but these are all very special statements of free Fermi gas. What is not a special statement is that the charge of the excitation changes as you cross the Fermi surface. So let's try to make that a bit more precise. So that's what I want to develop along the ideas of Landau. I mean, Landau, at least in his original papers, presented it something that came out of pure thought. And maybe it did, but I suspect there were many complicated two-loop calculations that he did that he hid from you and from us. And I'm also not going to do any two-loop calculations, but I will try to at least do something simple to formally justify what Landau postulated. But let's just proceed with Landau's postulates first. Okay. So the basic idea of Landau is one of adiabatic continuity. That is, you have some interacting system which has some ground state you'd like to understand, and you'd also like to understand its low energy excitations. So you turn on interactions. So the idea is adiabatic continuity. So you have a free gas, here's free, and here the ground state is product on K, E dagger K sigma, up and down. Here that's the KF acting on the vacuum. And you turn on interactions. So slowly turn on interactions. And that goes into some interacting ground state that we call G bar. And that's really one of the most important assumptions, that this is a smooth process, that along this way you don't encounter any singularity. Now, when you have a gap state, that's a much easier statement to make. You say that, well, if you can connect it without closing the gap, then you're fine. Here it's just a bit tricky because it's a gapless state. So what do you mean by adiabatic continuity? There's no energy gap slower to which you have to move. So it's a little tricky. So the arguments are not rigorous at all. If you had a gap, then this would be completely almost rigorous. But it's a gapless state, but you still assume there's some notion of adiabatic continuity. Okay, we just regard it as a postulate. We'll try to make a more formal justification soon. But nothing will be really proven. Okay, so this it goes to some ground state, and you don't know its wave function. It's something complicated. We certainly have a lot of experimental evidence that this is correct. I would say even for very strong interactions, this is correct in many cases. All right, so that's for the ground state. But suppose I do this for an excited state. So I add a particle, C dagger K, and of course here K has to be greater than Kf. And then I go here. So I'm going to go to some state here, and I'm going to call that state a quasi-particle state. We do have some other energy, which would be a function of the momentum K, E bar of K or something. So there's a quasi-particle that have charge +1, since I'm conserving particle number. That's key to everything here, conservation of particle number. If you had a lattice, well, then the momentum, well, okay. Yeah, if you have a lattice and the momentum is the energy is a function of vector momentum, and in general, but we'll have the same momentum here and there. Okay. So that's for a single quasi-particle state. That's how you define it. So that's what our single quasi-particle state is a state. And I want to be, I can do this for any momentum K. But where this is a good thing to do, as we'll discuss in a minute, is when K is very close to the Fermi surface. And you do the same thing with the hole. Now K is smaller than Kf. And that will go to a quasi-hole state. And it'll have some excitation energy, which I'm going to call as minus epsilon K. That's the excitation energy. And in fact, another assumption, which seems quite reasonable, and you can check with perturbation theory, that this epsilon K is the same function, just like it was the case here. This epsilon K was just a smooth curve, and we're going to assume, as you can check, at least the low order perturbation theory, that there's nothing singular happening at Kf. Actually, sometimes there are something singular, but let's not worry about that now. So you have a smooth function to begin with, and you have to flip its sign to get the actual energy. Okay, so there is then at some there is a notion of a quasi-particle state and a quasi-hole state related to some smooth function epsilon K, epsilon bar of K. Now this function will have then 0, which will define the Fermi surface, and but that epsilon bar of K is not the same function as epsilon of K. So the Fermi surface in general need not be the same. Now, one of the things we're going to prove, probably not today, next time, is that the volume enclosed by the Fermi surface is the same. Now, if you were in the continuum, where the energy is only a function of modulus of K, then in fact it's exactly the same. There's no, once you use the Leffinger theorem and use the fact that the energy only depends on modulus of K, and there's no change in the Fermi surface either. All right. So far this is relatively rigorous. Now Landau makes a further leap. The further leap is what happens when you have not just one quasi-particle or one quasi-hole, you have a million quasi-particles and a million quasi-holes. You can have those no problem because you are dealing with a very large system. So the question is that does this hold assume this also hold. When the density, number of particles per unit volume, or the density of excitations, not the number, but the density is non-zero, but it'll be small in some units. Of course, we don't want to describe all possible excitations. That's going to get into a lot of trouble. You can't do that. But we want to at least, we don't want to describe just one or two excitations. That's not thermodynamically significant in an infinite system. We want to describe a situation where there's a finite density. But we're going to take that density to be small. And the energy of those excitations also to be small. Again, the energy density to be small, or the number density to be small. Then does this process of adiabatic continuity still hold? And this claim of Landau is that yes, it does. Even for this case, when you have a low energy density and low number density of excitations, there is still a one-to-one correspondence between the excited states of the free electron gas and the excited states of interacting electron gas. So this is a much stronger claim because the number of such excitations is exponentially large. Once you have a finite density, you're really talking about the many-body Fock space, not the Hilbert space of a single particle. You have a system of size n, you're talking about e to the n states. So you're characterizing e to the n states by order n numbers, which is the number of quasiparticles. So that's a very strong assumption. Can you characterize this many particle states just by writing them and connecting them continuously to the free particles? So that's point number one, that adiabatic continuity holds not just for single excitations at the ground state, but also holds for a finite density of excitation. Yeah.
So before you turn on the convection,
Yeah.
the thing on the left-hand side is obviously an eigenstate of the Hamiltonian.
Yes.
And it has a dispersion relation.
Sure.
But with the interaction, it mixes with all sorts of other states.
Yeah.
So there must be some underlying.
So this is also assumed to be an eigenstate of the new Hamiltonian. That is, you're adiabatically turning on interaction in a way that you're able to stay in the ground state or that particular state.
Then why is it clear that there's a particle interpretation at all, even for weak coupling?
Right. I mean, this
I know
the
that
particle interpretation really, okay, this is just, at this point, you can just think of it as a label. There's a given state, which I'm going to call this, okay? I just, for each key, I've given you a state. And you obtain that state by doing this process. Okay, so that's a state, and you do it slow enough that it's a pretty good eigenstate of your Hamiltonian. I'm just calling it a quasiparticle. When it becomes a real quasiparticle, is the second assumption. When I say assume this is still true, which is a stronger assumption, which I have not justified, then it's more like a particle. Okay. At this point, I didn't really, the assumptions were relatively weak. This is where I'm really saying that where these labels are justified. Okay. Probably spending way too much time on this, but I can skip all this stuff, but it's usually not discussed in the textbooks, when I find the textbook discussions totally impenetrable.
Maybe you'll discuss it later, but isn't there also a story that the interactions are irrelevant as you approach the...
Yeah, okay, well, sure, you can, that's in the RG language that came much later. I'm just giving you my understanding of Landau's arguments, correct? Yeah.
But
That's also quite a subtle argument.
Without
I think that's
comment.
logical.
No, what I will, actually, I'm not such a fan of those RG arguments either. Really, the key thing is the lifetime, which I'll come to. The RG arguments, they're not really fully justified, I think, without the lifetime computation, which is not part of the RG arguments. Yeah, okay. I'll present it the way I think it's best to understand it. But other people, of course, have different opinions. Okay. So with this assumption then we can proceed. So let's assume that's true for now. So then you can ask, what is the energy of this many body state? This is excitation is a finite density of excitation. Well, your first guess would be just add up the energies of the quasiparticles. And what Landau pointed out, that's actually not true. There's an important correction, which is associated with the Landau parameters. But apart from that correction, everything is as if you had free particles with a modified dispersion. Okay, so how does Landau proceed? Okay. All right, so what we need to talk about then is we're going to introduce a quantity called the density of excitation, that momentum P. Which I'm going to call delta N of P. N of K, sorry, I've been using K today. And the way I'm going to define it, and this is why it's, you'll see again, because of this change in quasiparticle to quasi-hole, and this complicated change in epsilon sign, epsilon K, the way I'm going to define it, that N of K is equal to the density of quasiparticles outside the Fermi surface, and density of quasi-holes with a minus sign, sorry, for K less than Kf. Okay. All right, and this is just the density of these excitations that I've created. But I want to define a quantity which actually flips sign. And that's a bookkeeping device, there's nothing deep about it, but actually it just makes your life simple. If you define a function that also flips sign as you go through the Fermi surface, just like the excitation energy flips sign as you go through the Fermi surface. And then when you take the product, you don't have to worry about the sign. Everything comes out right. Okay. There's another way to say this, which is how in practice you do your calculation, is that you assume, but again, this is actually just a bookkeeping device, not a fundamental assumption or anything. Just to keep track of these minus signs. You say,
If
yes.
you didn't put the minus sign there, this would just be the charge density?
Yes, yeah. Right, so what we're going to say now is that the ground state wave function is exactly product on K less than Kf. This is actually as of some quasiparticle operator. So C quasiparticle, K spin up, 3 quasiparticles, spin down, acting on the vacuum. So these are some horribly complicated operators that we don't know much about. We have to normalize from the free particle operators in some way. And we're going to assume we can write the full ground state in this way. Now, in practice, this is actually not true because the quasiparticles are not well defined away from the Fermi surface. But we're only going to look at perturbations of the ground state near the Fermi surface, with both inside and outside. And near the Fermi surface, this statement is in fact correct. Okay, so, but you can ignore all of that. It's just a way to simplify your algebra. So if this is the case, if I plot as a function of momentum.
Excuse me, you're also assuming those satisfy standard canonical anti-commutation relations or not?
Yes. Okay, but since I'm not going to use them, I won't. Yes, but the answer is yes. Okay, so then I have the following distribution function. So here, what I'm plotting, this curve here is the NQP of K, which is the density of quasiparticles in the ground state. So by definition, this is kind of a strange thing to do, because a quasiparticle or a quasi-hole is really an excitation. So what I mean by I have quasiparticle in the ground state. Well, this is just some reference state I'm defining to make my life easier. I'm not really doing anything that shocking. It's just a definition, if you wish. Okay. So therefore, we're going to define the distribution function of the actual quasiparticle in the ground state to go from, sorry, this is 1, and then it goes to 0. Okay. Then I'm going to introduce, so this thing I'm going to call N0 of T. N0. Okay. All right, so then what about the actual, I really want to describe this delta N of K. So I'm going to introduce another function, which will turn out to be smooth. This I'm going to call N of K. And then my delta N of K will be N of K minus N0 of K. And so what you see now is if I take this function N of K and take this difference, then delta N of K is negative here. This is delta N of K. And positive here. And that's exactly this function over here. Okay. So my only purpose is introducing this N0 of K, which is just a reference, which I can subtract. And then I can work with N of K rather than working with N0, delta N of K. N of K is a smooth function that goes through the Fermi level. So that's really the only reason I say that the quasiparticle distribution function this goes from 1 to 0 to allow me to work with a smooth function rather than this horrible looking function delta N of K.
I have a question.
Yes, go ahead.
Is the vacuum of particles and the quasiparticles assumed to be same?
Yes, yeah, this is just the empty state. But the point is that this kind of definition may make no sense over here. It's probably true that down here at 0 momentum, the concept of quasiparticles makes no sense. My real assumption is that this kind of definition works in this window near the Fermi surface. And the width of this window typically will be the temperature in energy units. Sorry, this was energy. We can multiply by the Fermi velocity plus T over Vf. And in a typical metal, the Fermi energy, I don't know, it's 100,000 Kelvin, maybe even higher. And so at room temperature or below, this temperature is really a very small window near the Fermi. That's where we're going to apply it. Okay. So this assumption probably is not true here, but as long as it's true in this window, I'm okay. All right, so now that we have this delta N of K and this way of defining it, I can now write down the Landau free energy functional.
Just to make sure I understand.
Yeah.
It's not just that this definition doesn't exist or far from the Fermi surface. Even the C's, it's not clear to me how you define them far from the Fermi surface.
The C's of the bare electrons are, of course, very
No,
well
the
defined.
C's of the quasiparticle.
Absolutely, it's not clear.
So it's not just that the equality is not right, it's even the right-hand side is not well defined,
Yeah,
because the C's don't exist.
okay, I agree with you. So, right, so in the end, what I'm saying, this is not well defined, this is not well defined, but the difference is well defined. That's what, and I only care about the difference. Yeah, these are the kinds of gymnastics that are buried in Landau's paper. Okay, so now I can write out the Landau functional. So that he said, well, so you're given some delta N of K, which gives me the density of quasiparticles and quasi-holes. So there's going to be some energy which will depend upon delta n of k. So we have some many body excited states of the system. And what is its energy? Well, your first guess would be, well, you just add up the energies of the quasiparticles, which I call E bar of k, times delta n of k. Okay. And that is indeed the first term in the Landau energy function. But let's ask, how large is this term? Well, so what we know is that delta n of k, if you're at, say, thermal equilibrium, is appreciable for the excitation energy E bar of k of order temperature. Because at temperature T, you're going to excite particles at energy of order temperature. And similarly, E bar of k is also of order temperature. Appreciable, sorry. So this number is of order 1 in this window, but the range of that you have to, so appreciable for, right. So this happens for, so this is true for this energy VF K minus KF. VF is some Fermi energy of order temperature. Okay, so when I'm doing this integral, sum over K, I have two factors of temperature. I have one factor of temperature from the radial integral. So I have some Fermi surface here as a function of Kx and Ky. And I'm getting some excitations here. Okay. So things are excited. The things that are excited have energy of order temperature. That's this factor. And the window that I have to integrate over, this is temperature over Vf. So in fact, the correction to the total energy due at a finite temperature T is going to be of order T squared. So this thing is of order T squared. Not of order T, as you must naively think, it's T squared. It's doubly small because you have to account for the fact that the low energy excitations only occur in a narrow window of phase space. Now, if you had Dirac fermions, it's even smaller, T cubed or T to the D plus 1. This is more like a one-dimensional Fermi gas. And that's because you only have to worry about the radial direction. Along the angular direction, it's a zero energy contour.
So you're just saying that the density of excitations is of order T, and each excitation has an energy of order T.
No, so the delta n of k is about a 1, as you can see over here. It's a range of momentum of which is its non-zero is of order T. This is of order 1, this is of order T, and dk is of order T. Okay, so
Is it T squared over Fermi energy, just to make the energy?
yes. So the relative correction is T over the Fermi energy squared on the free Fermi gas. Sorry about that. It's also true for the free Fermi gas. You can just compute it. All right. So, but that's not the entire Landau function. So what Landau pointed out, well, there's another term which is doubly small, which is the product of two delta n's. 1 over 2 volume, sum on P K, FPK. So this is called the Landau parameter or Landau function. Usually you decompose it in various angular momentum components. Delta n of P, delta n of K. So what we find here is that the quasiparticles do influence each other. If there's a bunch of quasiparticle already there, if I create one here, it's going to feel its energy is going to be different. The total energy system is going to change different. There will be some interaction between them. And this is also order T squared, because although these are of order 1, the window of temperature over delta n is appreciable with order temperature, and you have two radial temperature intervals. And so this will give you a T squared term. Okay, so this looks like an interaction between the electrons. How is it different from the original interaction that I wrote down in the Hubbard model? What is really special about this? What's really special about it is that it's entirely forward scattering, thinking of scattering the net. So you have some interaction. If I write this out in the bare electron operators, this is C dagger P, CP, C dagger K, CK. So if I want to think of it in some interaction language, I have a particle here and a hole here with momentum P, and P, they interact with FPK, and then I have another particle on hole. Now, if this was a true scattering process, even if the center of momentum here was the same, there were P and minus P, there'll be a Q and a minus Q here in general. So there is no momentum transfer. This just involves a number of particles. So delta N of P, the number of particles, each momentum is conserved. So the important property of this is that the number of particles at each momentum K is conserved. So we've got an infinite number of conservation laws that we didn't have before. What we had before in the Hubbard model was that the conservation of total number of particles. Now we get to low energy theory of Landau, and this theory has an infinite number of conserved quantities, the number of quasiparticles. If this is my energy and therefore corresponding Hamiltonian for time evolution, which is the kind of calculation you have to do, then that Hamiltonian will conserve the number of particles at each momentum K. So this is an emergent conservation law, which is only true at very low energies, very close to the Fermi level. And the RG argument that Juan mentioned, that's what the RG arguments show. You do some RG and you find that the forward scattering term is the one that dominates.
The scaling argument you just gave does not prove that. No.
I haven't proven anything. All right, so what, somehow I have to, the main assumption here that's underlying this is that the description of the many-body Hilbert space in terms of the product of quasi-particle states is valid, that in over some energy range, in some approximation. And that involves doing a calculation, which I haven't done, which is not part of the RG argument either, but I will get to, maybe not today, of looking at the lifetime of these quasiparticles. So there's another term in the Hamiltonian, which would be a correction, which asks the question that suppose I create a quasiparticle, how long does it last before it decays into another shower of quasiparticles and quasi-holes, and then systems become thermalized and chaotic, and the concept of quasiparticle doesn't hold. And the point Landau makes is that this kind of decomposition is valid as long as the time it takes for you to lose the lifetime of the quasiparticles is much larger than its inverse energy. Basically the width is larger than the mean energy. And that's not something I can estimate from anything on the board. I have to do an independent computation. And that's really a correction to Landau's Fermi liquid theory, and those corrections are small. There are small, even higher order corrections, higher powers of T over E. Okay, so that's my best understanding of Landau's postulates, and they seem rather mysterious, and I have no doubt that Landau did many more complicated arguments that were not in his paper or computations to establish that, and I'll try to turn to some similar computation in a minute. All right, so you can now start from this energy functional and compute various things. You can compute the specific heat, you can compute the compressibility. That's fun stuff, that's in the notes. And it's in every textbook. And I'm not sure I want to go through it. I'd rather go to the more formal discussion of Fermi liquid theory using Green's functions and move towards establishing fundamental theorem, which is also implicit in this discussion. Well, maybe not. It's not really needed essentially for anything I've said. That the volume enclosed by the Fermi surface is an invariant under this adiabatic evolution. Any questions in India? All right.
One naive question. Can you say something about the zero sound from this energy functional?
Yes, you can work it out. Let's see, you have to write down some equation. Let me see if I remember this. Yeah, okay, I may have to defer to next week, but yeah, you start with the energy functional and you write down equations of motion. I think you just have to need one set of commutators for the density fluctuations. And you can get zero sound excitations from this, yes. That's a great question. I shouldn't be able to answer that but on my feet, I'm forgetting exactly how it's done. I'll try to answer that next week.
For the time being, can you tell us what is the zero sound physically in terms of the original electron density or something?
It's just a density. So it's in fact, yeah. So I should really have been better prepared for that. So, first sound is sound in the air, which is a hydrodynamic mode of density fluctuations with lots and lots of collisions of particles. So it's not an it's really property of fluid dynamics. And it's interesting to remember that first sound was understood even before people knew there were molecules. It's just a property of some fluid which just conserves momentum and equilibrates, which is what happens when you have lots of collisions. So first sound is very different from zero sound and second sound. The second sound is the density fluctuation. It's a coherent excitation in a superfluid. And zero sound is again exactly the same. It's a coherent excitation, which in a Fermi gas, without long-range interactions. If you have long-range interaction, it becomes a plasmon. But in a Fermi gas like helium-3, there will be a zero sound mode, whose energy also goes to zero as K goes to zero. So its existence and the fact that its energy goes to zero as K goes to zero doesn't have an interpretation in terms of a broken symmetry. There's no broken symmetry, but it does have an interpretation in terms of the Fermi surface. So it is a fundamental collective mode of a Fermi liquid, and I'm not sure of any broader interpretation of why it's gapless, but it is. I will answer that. That's a great question. I'll try to answer that better next week. Yeah. But these are the basic, there's zero sound, which is in a Fermi gas with short range interactions. First sound in air, that's how I'm speaking. Second sound in a superfluid. And third sound and fourth sound are various surface modes. And I don't know. I think at some point people didn't stop using that word. But all of them, except first sound, are actually coherent collective excitations, not hydrodynamic modes.
Subir, there were some questions about the nature of these quasi-particles and what kind of interactions are allowed within this framework. Are they short-range interactions in some way? And
well, the interactions are defined on the lattice model. I took a Hubbard model. I could have taken something with short-range interactions. You can even take Coulomb interactions, and all of this goes through for Coulomb interaction, which is long range. But in the Coulomb interaction case, you have to keep an additional term, which is not here, which will account for the long range part. So it's really relatively easy to keep that because it's just ordinary classical. With Poisson's equation, you can keep track of it by putting an electric field that's created by any density fluctuations. So apart from that, the interaction between the quasi-particles, at least at low temperature, are these functions Fp of K. So these functions, I should mention, are defined only on the Fermi surface. So this delta n of P and delta n of K are appreciable only near Kf. So in this evaluation, you can in fact pull out the radial integral, pull out Fpk out of the radial integral. And so Fpk is really only a function a function of P and K on the Fermi surface. So if you're in, say, 2 dimensions in the continuum, it's only a function of an angle, well, 2 angles. But if you have translation invariance, can only be a function of the difference of the angle. So in the end, it's just a function of 1 angle in the continuum without a lattice. In 3 dimensions, it's convenient to decompose into angular momentum modes, and so you have F0, F1, and so on. On the lattice, there's no constraint. It's you have to just know the function.
Thanks.
And one of the tasks of theorists is to start from some Hubbard model and compute this function. You can do that numerically. You can do some DMRG or something, and I think some cases you can do it, but usually that's a hard problem. In practice, what you often do is you measure this function in experiment. And then in helium-3, for example, you measure some angular momentum component of FPK in an experiment. And then you can compare different experiments like the compressibility, specific heat, zero sound, define in different ways on the same function F. And then you can look for consistency between them. And that's the kind of thing that, especially in helium-3, has been done with great success. Okay, thank you. See you next week then.
Much time calculation basically the same as the RG argument?
No, that's a 2-loop calculation, it's not part of it.
No,
The RG argument just tells you dominance of forward scattering. It doesn't give you the lifetime.
and forward scattering doesn't allow the quasi-particle.
That's correct. Yeah.
That's the fact of the higher dimension operator, the fact that the other operators are relevant.
Yeah.
I strongly recommend Wojcinski-Stasi lectures.
I
It's written in our language.
Yeah,
and it addresses precisely
but I
this
think
point.
but I think that this is what we were saying, that Joe does a one-loop calculation
That's right.
talk about to establish relevance and irrelevance, but Sabir is saying that the lifetime is a 2-loop. It's not literally the same.
But that might be an iteration of the one loop. It might be really one loop in this class.
What I was saying is that you need the non-forward operators to allow the quasi-particles to decay. And the fact that the non-forward operators are relevant means that the quasi-particle lifetime.
Yeah, but I think there's an issue that since there's an infinite number of non-forward operators, this is kind of delicate. You have to do the calculation.
I see. It's because of the continuous index.
Yeah, it's a whole, it's not that, I think it doesn't.
So I looked also at Shankar's paper, which preceded, and I didn't understand a word. And Joe says, this is my understanding of what Shankar did.
Yeah, okay. I was talking to Shankar Taylor and writing his article, and it's a very nice article, and I'm not saying anything wrong, but you have to do a bit more to fully establish the consistency of the theory.
But it is a remarkable simplification.
But you're saying the issue is the fact that there are an infinite number of irrelevant operators.
Yes, I think you could say it that way. Yeah.
Fair enough. Yeah.
Well, that's often the case. I think the surprising.
No, the same dimension of relevant operators. Yeah, that's right.